Welcome to the Purdue Applied Thermofluids Laboratory YouTube channel. Today I'm going to show you how to simulate thermal runaway of a single lithium-ion cell using the Hatchard-Kim reaction mechanism and 0D lumped body approach. The problem setup is shown here. We start with a single cylindrical lithium-ion cell at temperature T0, placed in an oven at temperature T infinity. Over time, the cell heats up from convection and radiation until the cell enters thermal runaway. The model framework is based on the conservation of energy equation for a solid motionless body, shown here. On the left-hand side, we have density, volume, and heat capacity of the cell, and the time rate of change of temperature of the cell. Now, this formulation follows the lumped body approach, also known as a 0D formulation, where the body of interest, in this case our battery cell, is treated as a single control volume. In other words, we're not solving for temperature gradients through the cell. We have one temperature, which represents the temperature of our cell. On the right-hand side, we have two different source terms. One is shown with a summation sign, Q dot with subscript Rxn, I. This source term represents the internal heat generation from decomposition reactions. In our model, we have a number of different decomposition reactions. The ith reaction will have a source term shown here in this bottom box. Wi is the mass of reactants per unit volume. V cell is the volume of the cell. Delta Hi is the enthalpy of reaction. All of these three, when multiplied together, will have units joules. And Ri is the reaction rate, which has units of 1/seconds. So in a unit balance, we then have watts on the left-hand side. The other heat source term is due to external heat transfer between the cell and the surroundings, and we can see the convection term and the radiation term. The reaction rate of the ith decomposition reaction is shown here and follows an Arrhenius type expression. The kinetic parameters are A, frequency factor, Ea, activation energy, X, dimensionless amount of reactants remaining, N1 and N2 reaction orders, and Gi, a reaction modifier. The reactants will change over time according to this ordinary differential equation. dx over dt is equal to C times R. In most cases, C is just a -1, which indicates that the amount of reactants decreases over time. For some reactions, X represents the progress of reaction and increases over time, in which case Ci would be +1. The reaction mechanism to be used in this example is known as the Hatchard-Kim reaction mechanism, which follows two key works, one by Hatchard et al. 2001 and one by Kim et al. 2007. The four reactions are SEI decomposition, which will be abbreviated SEID, anode electrolyte reaction, ANE, cathode decomposition, CAT, electrolyte decomposition, ELEC. The four reactions are shown here, and each reaction has its own set of kinetic parameters. In most cases, C is -1, except for the cathode decomposition reaction, which is +1. The initial amount of reactants is shown as X0. SEID, ANE, and ELEC will all decrease, and the reaction will stop when X reaches 0. The cathode reaction begins at, in this case, 0.04 and will increase until this value reaches 1, and then the reaction will stop. Each reaction has just a value of 1 for the G reaction modifier, except for the anode electrolyte reaction, which has a reaction modifier shown here, exponential of -TSEI over TSEI0, where TSEI is known as the SEI layer thickness and changes over time at the same rate as the anode electrolyte reaction rate. So we have an additional ODE, which says that the rate of change of TSEI is equal to the anode electrolyte reaction rate. So over time, this value will increase, and this term will decrease, and the rate of the anode electrolyte reaction will slow. So there are some interesting dynamics between the coupling of these two ODEs. The last part of this model is simply the thermal parameters, which you can see here. I'll make one note that the surface area used for convection and radiation is the outer cylindrical area, and we did not include the ends of the cylinder. Of course, they could be included if you wish to. In this case, it is assumed that the ends are insulated. Okay, I have switched over to the Simulink model, which is organized into different panels. I'll walk through each panel one by one, starting with the model inputs. Here we handle the cell geometry and thermal parameters of the model. I mentioned that this model is set up for a cylindrical cell, which requires a radius and length to define the geometry. If you're interested to study a prismatic or some other format, you're welcome to change the geometry as needed. Similarly, if you're interested to change the thermal problem, you can change the thermal parameters as needed. Next, let's talk about the conservation of energy panel. Here, the 1/S block shows the integration of the time rate of change of temperature, dT/dt. So integrating that time rate of change of temperature gives us the cell temperature throughout the simulation. T cell 0 is the initial condition. In this case, the simulation runs from time 0 to time 5,000, and if you're interested in a different length of simulation, you can change this. The units are in seconds. The rest of the math going on in this block is solving and rearranging the conservation of energy equation to reduce ordinary differential equation down to dT/dt. So we have the heat generation from each of our four reactions, which when summed together gives us QRxn. We have our external heat transfer, and we have some cell thermal parameters here. We can also integrate the reaction heat rate over time to get the energy released from our decomposition reactions. The external heat transfer is shown here, radiation in the top grouping and convection in the bottom grouping. Summing those together gives us our total external heat transfer rate. Now there are a series of 4 purple blocks representing each decomposition reaction. I'll show the SEI decomposition reaction, and they all follow the same pattern. The equations are assembled, and very similar to the conservation of energy ODE, we have an ODE here which needs to be integrated. We can see the integration block. We can see the initial value, in this case 0.15, for the initial value of SEI decomposition, X, the X value. It should be noted that the reaction rate is pulled off here and is used to calculate the reaction heat. We have some additional parameters needed to calculate that rate of heat generation. The R, the reaction rate, is then multiplied by C. That's our bookkeeping parameter. Either it's a +1 or a -1, depending on the reaction. Over here we have some reaction orders, and really the rest of the ordinary differential equation is here. So each of the 4 decomposition reactions follows the same pattern. Here we can see the heat generated by anode electrolyte, heat generated by cathode, and heat generated by the electrolyte decomposition reaction. And there's one more block to show, which is model outputs. Here I've taken the different go-to blocks and dropped them as a from block. And each of these different parameters is put together into a single bus and then dropped in this out.sim out. And what that does is stores all of this data to the MATLAB workspace, and you can work with that in post-processing. You could also use scopes like I have here. So let's go ahead and bring up the scopes, the reactions on the left, and the cell temperature on the right. On the left, we will have the X values for each reaction, and on the right, we will have cell temperature, and I'll go ahead and run the model. Okay, and the model has completed. And we can see the cell temperature rises slowly from convection and radiation. At a certain point, the cell temperature increases very rapidly. That is your thermal runaway event. and then the cell cools down back to the oven temperature after the thermal runaway event. If we look at the X values for each decomposition reaction, we can see SEID starts at 0.15 and drops to 0. Anode electrolyte starts at 0.75, it starts dropping, it doesn't fully reach 0. That reaction actually slows to a great extent because the thickness of the SEI layer, which is the orange line, increases rapidly, and if you remember, as that value increases, the rate of reaction for ANE decreases. The cathode reaction starts at 0.04 and increases up to 1 and then stops, and then finally the electrolyte decomposition starts at 1, it progresses very rapidly down to 0. We can zoom in on that to take a closer look. You can see how rapidly that electrolyte decomposition reaction occurs relative to the others. That's it for this video. I encourage you to open the model. I'll provide a link in the description of this video where you can download this Simulink model for free and try it out yourself. Thank you very much.